So for our executive summary for the open channel flow measurement using a Weir and Orfis lab, we used 3 different apparatuses to carry out the experiment. We used the HM150 to test the rectangular weir. We used the BM16 hydraulic bench to test the V-notch weir, and we used the HM111 to test the orifice. Throughout these tests, we were testing for the coefficients of weir and orifice. To determine those, we use the following equations. Here, this is for our rectangular sharp-crested weir. Q equals CW BH to 3/2, where B is our base width and H is the height above the water. Here we have the V-notch weir, and here we have the orifice. These equations were used and calculated to analyze our flow rates in the open channels. Our results were as followed. The average flow rate for a rectangular weir was 3.33 CFS, and our results were 4.6. For V-notch was 1.84, and we got 5.12. And for orifice was 0.6 average, and our results were 0.64. So for our introduction, we're going to summarize our relevant theory for this lab. The theory is for both the weir and the orifice can be analyzed using the energy equation for varied flow. Some assumptions we make are there's negligible losses and a small upstream velocity. So the relevant theory is if we use the energy equation, Bernoulli's equation, we can write out these following equations where Q equals CWB times H to 3/2 for a rectangular weir. We have Q equals CWH to 5/2 for a V-notch weir, and we have Q equals CD times A times 2G times H to the 1/2 for an orifice, where B is the width of the base, H is the height of water, and A is the area of the orifice. So using these equations and the theory that we can use these equations, we can carry out our lab experiment using the 3 apparatus in the lab. So using the 3 apparatus, which are the HM150, the B16 hydraulic bench, and the HM111 hydraulic bench, we can carry out multiple tests to find a value for our average coefficient of weir and orifice. So an average value is 3.33 CFS for a rectangular, and our results were 4.65. For V-notch, the average was 1.84, and our results were 5.12. For orifice, the average result 0.6, and our result was 0.6. So these values obviously depend on the site condition, and these assumptions that we make that the upstream velocity and the head loss is negligible obviously depends from open channel to open channel. When you go out and you see a concrete open channel, some concrete be rougher than others, or just there's different variables that change up what these coefficients obviously are. But overall, we can use these apparatuses in the lab to simulate a common open flow channel.
Keep going. I'm holding it. No, it's got to go all the way down.
20 millimeters. Done.
Now we're gonna discharge valve. Now we're gonna record the volume over time.
Are you gonna just still do 1 liter? How long it takes for 1 liter?
Alright, we're gonna be ready to start it and start there.
John, you still wanna do 1 liter? So 1 liter?
So wait for it still when it goes 4 liters, and then we're gonna stop.
To get to this point, we unscrewed this thing right here, lowered it down.
And we took the midpoint of the circle, which is right around here.
Put your finger back a little, yeah. So the center of that.
And then we're gonna back it up right here. And we're gonna turn her on.
Stop.
9.47 over half the read. So this is the discussion part of lab number 8. This is the comparison of CW, CD, and head values. When trying to compare the values CW for the rectangular weir, it is generally known that the theoretic value is roughly 3.33. However, the experimented yielded 4.66. When trying to compare the values for the CW of a V-notch weir, it is roughly 2.5. However, the experiment yielded 5.21. Lastly, when comparing the CD values of a circular orifice plate is generally 0.6. However, when the experimented yielded 0.65. When looking at these values, the orifice was essentially right on. The rectangular weir was a little off because reading the manometer and the conversion chart could have been off. The V-notch could have been off because the measure was inaccurate due to the possibility that the measurement in height was a little bit off. The lab said to measure 20 inches, but we could have not been perfectly 20 inches back. The head term exponent for the rectangular weir was 1.5. The V-notch weir was 2.5, and the circular orifice plate was 0.5. These head terms are based off values that are based off the curve. Due to the curve being exponential, the value shown in the exponent is represented as the head term exponent. The higher the number is, the more steep the curve is. So I guess it correlates. This exponent shows how much head can be generated. If the curve is steep, it represents that the flow produces a lot of head. When reading the pump curve, many times the pump will have a low curve, which means there isn't much head. However, it has a high flow rate. On the other hand, flow can have a high pressure and have a low flow rate. When reading these graphs, we can find a good balance between the two flow rates and pressure. And this is the analysis and source of error. Originally, in the experiment, the group had some trouble starting the lab. There was technical difficulties with the weirs and the orifice. These inconsistencies could have led to a difference in values, but however, the students, we all followed the lab procedure strictly, and there wasn't any missteps. Some other forms of error or variation in the lab could be in measuring the height. For example, when we were supposed to get the midpoint of the orifice plate, it was conducted by eye to see where the midpoint was. This could lead for a source of error because it was not perfectly set in the midpoint. So we said in all weir tests the height could have been off as much as 5 to 10%, which can lead to a variation in the results. Other sources of error could be in the flow rate calculations. Since flow rate had to be calculated, there could have been error in the timekeeper. The time could have started before or after the intended time, and it could have been off by milliseconds or a full second or anything. It definitely wasn't perfect. All the equipment was in good condition, so there was no inconsistencies in the equipment itself. And historically, broad-crested, sharp-crested V-notch weirs and V-notch weirs are used in hydraulics and hydrology to determine flow rates and open channel flow. As seen in our lab data, sharp-crested weirs are more accurate, but can be difficult to build for larger projects. V-notch weirs are accurate only in smaller streams or smaller projects, like watersheds. Consequently, orifices of the different sizes are commonly used in detention basins in order to restrict flow.